Hey everyone, and welcome to this explainer. Today, we're going to unpack those invisible physical forces that completely dictate why things around us either sink like a stone or just float effortlessly on the surface of a liquid. It's this fundamental piece of everyday physics, but honestly, we rarely stop to actually decode it. Right, so let's dive straight into this kinda counterintuitive mystery. What truly determines if an object sinks or floats? Is it just about how heavy it is? We naturally tend to assume that heavy things sink and light things float. But think about it for a second. A massive steel cruise ship floats perfectly, but a tiny little steel pebble sinks instantly. So clearly, weight alone is absolutely not the whole story here. To get to the bottom of this, here is our roadmap. 1. Unpacking density. 2. The rules of floating. 3. The power of upthrust. And 4. Solving fluid puzzles. All right, let's kick things off with section 1. Unpacking density. The absolute foundation of this entire explainer boils down to this one simple, yet incredibly powerful formula. Density equals mass divided by volume. Simply put, density is just mass per unit volume. In plain English, it's a standardized mathematical way of measuring exactly how much stuff is crammed into a specific amount of space. And this perfectly illustrates the math on a microscopic particle level. When you have closely packed spheres arranged in a tight, rigid grid, well, that represents a super high density. But then, if you take that exact same amount of volume and spread the spheres out, you have far fewer particles and lots of empty space. Basically, the more closely packed the matter is, the denser the overall object. Let's put that into perspective with some real-world numbers here. Density varies wildly in reality. Take the air inside a balloon. It's incredibly sparse, coming in at just 1.2 kilograms per cubic meter. But then compare that to a piece of wood, which sits at a much higher density of 893. And then check out the aluminum sheet. That is tightly packed matter, giving it a massive density of 2,700. So density gives us this perfect lens to compare radically different materials. Moving right along to section 2, the rules of floating. So what happens when we drop these objects into a fluid environment? Well, this setup establishes the basic ground rules really clearly. We've got 3 distinct situations happening at once. One block is just happily floating right on top, another is hovering perfectly suspended in the middle, and the last one has plummeted straight to the bottom. Why exactly does this happen? It turns out floating is literally just a game of comparisons against water's baseline density, which is exactly 1,000 kilograms per cubic meter. It's that simple. If an object's density is less than water's, like a piece of wood, it floats. If it's exactly the same, it perfectly suspends. And no surprise here, if its density is greater than 1,000, like a heavy rock, it sinks straight to the bottom. Okay, on to section 3, the power of upthrust. Now we are entering Archimedes territory. See, when an object hits a liquid, the liquid doesn't just passively accept it. No way, it actually fights back. It exerts an upward force on the object that we call upthrust. And the really cool part? The magnitude of that upward push is precisely equal to the weight of the fluid that gets shoved out of the way, or displaced by the object. This is a pretty memorable way to anchor the concept. When you have a small weight, it only displaces a little bit of water, right? So it only gets a minor upthrust. But then look at the massive elephant. It's creating this huge downward weight, forcing its block to sink deeper and shove a huge volume of water out of the way. And that massive displacement, it generates an equally massive upward upthrust to keep the elephant's feet completely dry. It's a perfect balancing act. Finally, let's wrap up with section 4, solving fluid puzzles. Let's actually put this math to the test with a completely submerged copper block. First, we need its mass. We take our density of 960, multiply it by the volume of 10, and boom, we get 9,600 kilograms. Now, gravity is obviously pulling that mass downward. So, multiplying by 9.8 gives us a massive downward weight force of 94,080 kilogram meters per second squared. Okay, so that's the downward pull. But what about the water pushing back? Since the block is completely submerged, it's displacing its entire volume, all 10 cubic meters of it. If we multiply the water's density of 1,000 by that displaced volume of 10, and then by our gravity constant of 9.8, we find the water is generating an enormous 98,000 newtons of upward thrust. Let's synthesize all of this together with one more real-world example. A square pine raft floating in a swimming pool. Our puzzle here is to figure out exactly how much of this raft, which we'll represent with a tiny height h, is actually sitting beneath the surface of the water. Because the raft is floating perfectly, we know for a fact that its downward weight must be exactly equal to the upward upthrust of the water. They cancel each other out. We know the raft's downward weight is 23,520, so the upthrust has to match that. We build our upthrust expression using the submerged volume, set those two opposing forces equal to each other, and when we solve for h, it turns out just 0.15 meters of the raft is actually underwater. Make sense? So, take a breath. You now have all the strong cognitive scaffolding you need to tackle these complex, fluid puzzles entirely on your own. You know exactly how density dictates floating, and you can map out that invisible tug-of-war between weight and upthrust. Which brings us to our final provocative challenge. Imagine a granite cube with a density of 2,500 hanging from a Newton meter and lowered into water. The tension on the meter decreases by exactly 0.02 newtons, which, by the way, tells us our exact upthrust. So using everything we've explored today, can you reverse engineer those invisible forces to figure out the exact physical size of this granite cube? I'll leave you to chew on that one. Thanks for joining me on this explainer, and keep questioning the fascinating physics of the world around you.